Hello students, this is a brief overview of how to address questions that ask us to predict the change in entropy for the system or for the surroundings, or to predict the sign that will be on the change of entropy for the system or for the surroundings. First, to predict the change of entropy of the system, it will all be based on our understanding of entropy. So we're going to go through that deeper after we address how do we predict the change of entropy of the surroundings. The change of entropy of the surroundings is determined by the heat flow of the chemical reaction or of the physical process. So chemical reaction, if we're forming new products with totally new identity. Physical process, if the substance or substances is simply undergoing a phase change. If the chemical process or the physical change is exothermic, well then we know heat is given to the surroundings by that process. Well, that should increase the disorder, the randomness of the surroundings. In fact, if we look at this equation, the entropy change of the surroundings is based upon the negative change of enthalpy of the system divided by the temperature. If the system is exothermic, we know that the change of enthalpy is negative. So then this will make the change in the entropy of the surroundings positive. If the system is undergoing an endothermic process or reaction, we know that means heat is being taken from the surroundings. Well, that should decrease the randomness or the freedom or the disorder of the surroundings. Therefore, the change of entropy of the surroundings should be negative. If the change of enthalpy of the system is positive, if it is endothermic, that will make the change of the surroundings entropy-wise negative. So it simply is looking at, are we giving heat to the surroundings? If it is an exothermic process, well then the entropy of the surroundings is increasing, positive. If it is endothermic, then we are decreasing the disorder, the randomness, so the change in entropy of the surroundings is negative. Now on to the system. All that we have to do is examine the physical states as well as the number of moles of each physical entity to be able to judge the change in entropy from reactant to product. For example, here we are taking gaseous reactant, but it is a total of 4 moles of gaseous reactant. And we are creating gaseous product, but simply 2 moles. So we are creating less gas, less disorder, less randomness, less freedom, so the change in entropy of the system is negative. We are decreasing, or we are increasing order. Here we are taking solid, and yes, we're creating more solid, but gas. So we are increasing disorder of the system. Here, gas to gas, but 1 mole to 2 moles. So we are increasing the amount of gas, thereby increasing the chaos, the randomness, the freedom. So increasing entropy of the system. And then, let's see, we have 3 moles and 2 moles, so we are decreasing. Now what if there was a tie? Well, we'd have to be given other information. So if we had 3 moles and 3 moles, 2 moles and 2 moles, we could not conclude upon the sign. We'd have to be given more information. In thermodynamics, it is usually the change in a certain function that's important. We're looking at where do we end up versus where do we start. So if we are negative in our change of enthalpy, we know that it is exothermic. If we are positive, we know it's endothermic. So again, we're looking at where do we start and where do we end, our state functions. If delta G, we don't know that yet, but if it is negative for the process, then we can conclude with confidence the process is spontaneous. If it is positive in its change in Gibbs free energy, it is non-spontaneous in the direction that it's written. However, we can assign an absolute entropy, an S, not a delta S. We assign that for what we identify as a perfect crystal. Well, that is non-existent. It is ideal. A perfect crystal is one in which every ion, every atom, every molecule has its place. If it is a cubic crystal, every distance, oh, you know how good I am at artwork, every distance is identical. There is nothing that is out of place. Perfect. Well, this then would have zero disorder. It would be absolutely ordered. Well, that is where the third law of thermodynamics comes in. The third law of thermodynamics tells us that the entropy of a perfect crystal, non-existent, just theoretical, but that could only happen at 0 degree Kelvin when there's no molecular motion or atomic motion, well, the entropy then would be 0. And the entropy would be equal to 0, and the common units are joule per Kelvin mole. From this then, at Kelvin, we then can calculate the standard condition entropy values. And of course, at standard state conditions, it's room temperature and 1 atmosphere. That is where we get all of the values that are in Appendix 4. And in your folders, or in the back of your book, is Appendix 4. The standard entropy values for all of our substances alphabetically is the third column. And again, the unit is joule per Kelvin mole. Please be careful, because the enthalpies of formation and Gibbs free energy of formation are in kilojoules per mole. And so we're going to have to just make sure that we identify that for any converting purposes, of course. Notice all of these values are larger than 0. They also are positive, because we are going to have some kind of randomness, some kind of disorder if we're not at absolute 0. If you look at your substances in Appendix 4, if you compare solid to liquid to gaseous state, you'll notice that your entropy values will increase as we're going from solid to liquid to gas, confirming what we would predict for the entropy values as we're going toward gas or the more disordered state. So because we can get entropy values, we have, just like we do for enthalpy, this summation equation. So we can actually calculate the change in enthalpy for a reaction by summing up the absolute enthalpies at standard state of products minus the absolute of reactants, taking into account the coefficient moles of the reaction. So I have an example here to take a look at. What I did for this reaction was found the standard state entropy values for each of the substances. That's what these represent, joule per Kelvin mole. And then taking product minus reactant. Now, we have 2 moles of SO2 times the 248 joule per Kelvin mole. And we would add that to 2 moles of the 38. Subtract from that the 2 moles for the nickel plus 3 moles for the oxygen. And what we end up, being careful of our algebra, now officially moles should cancel because we multiplied through by the coefficients. And for this, you should get negative 149 joule per Kelvin joule per Kelvin mole per the chemical reaction. Now, if we take a look, we would predict that our entropy would be negative for this reaction because we are taking solid, 3 moles of gas, making 2 moles of gas and more solid. So if we look at gas, we are decreasing the moles of gas. We are decreasing our change of entropy we would predict. So it's nice to get a number that backs up what I previously led us through. If you walk through and do the calculation for this reaction, you will get positive 179. Now, we would need to actually do the calculation because we have 3 moles of gas to 3 moles of gas. And so it would be hard to predict. I mean, we could look at, we have 2 moles of solid from 1 mole of this more complex solid. So we would expect that that would increase the entropy possibly, but we'd really have to calculate it numerically to be able to predict the sign. If you take a look at these questions that I left for us, we really want to be able to address not only these questions, but more importantly, these first. So if you read through this should confirm what I said. Here, the correct answer for 8 is B, because you are starting with just solid, making solid but 3 moles of gas. Nothing else compares. Nothing else creates as much disorder and randomness. The answer for D, negative entropy, would be decreasing. We are taking in D 3 moles of gas and making 2 from it. The answers for the other multiple choice, number 1 I wouldn't worry about, but number 2, 3, and then what would be number 4? Let me just put it here so you can pause, check my work with yours, and I, of course, can address any questions that you might have. Please email me or wait until the next class. Thank you, students.